Everyone knows how to turn off the notification sound in Zoom. I think this has been beeping like in the past. Anyway, so I'll figure it out.
Your whole volume. Maybe like turn off the volume.
I can mute my volume. No, people might ask questions. Right, okay, yeah, so we have a lot of things to figure out. So, why are you guys here anyway? I was planning to speak to okay, yeah. Last option, last opportunity to see me afterwards, right? So okay, so let's start. And as many of you might have received the email, and the new campus guideline was published less than an hour ago, and so I'm glad that we were in front of the schedule. So the scrambling was done on Saturday. I think that was good. So if this works, we're, as I said, the experiment is this Wednesday. I won't be here, and we're going to do exclusively through Zoom. And today, you should see the lectures from Courses Capture, as well as it's a YouTube video. Hopefully, it's not too large. I hope I'll be able to upload to YouTube. And I don't know either when 500 people or so ask questions in Zoom. Yeah, let me say that everyone who is joining via Zoom, please mute yourself. Okay, it's very important. For ask questions, you can turn on and see what I can hear. I think Zoom may have an option which is to raise hand. But I don't know while I'm writing whether I'll see this. Yeah. So this week is really exciting. Any question? Anyone remotely? Good. I also after this try to figure out how to stop this few hundred beeping. Yeah. Okay. So warm up problem. A is really 2 by 2 matrix. And x is a vector, and I ask you to compute a to the 1000th power. So you may, if I ask you to compute it once, compute it twice, you probably know how to do it. But this is 1000th power. Give a minute to think about that. A good option maybe just compute it. I mean, first compute AX now and see whether you can observe something interesting. Okay, so let's work on this. So this is, we'll just compute it, just try compute a times x naught, and this is 3, 3. This is something interesting because this is a 3 times x naught. That is, normally when you apply a matrix and multiply it to a vector, the result should be just some completely different vector. But because I chose a very special vector, later in the class you will know why, which is 1, 1, I found that it only scales the vector. All this matrix does is not a scalar matrix. It's not a 3, 0, 0, 3. Okay, but when applied to this vector, all it does is to scale x naught by a number. This is great because then a square x naught is nothing but 3 squared or 9 times x naught, and we can do the induction. A to the 1000th power times x naught, and this is 3 to the 1000. It's an enormously large number. I don't know what's the exact value, but I can write down the exact answer. Any question? So you might wonder whether there's something special to this x naught. The answer is obviously yes. Try, for example, x naught equal to 1, 2. You're going to struggle how to compute this a to the 1000th power applied to 1, 2. And the reason why this is particularly simple is because x naught is actually a so-called eigenvector of A. When x is an eigenvector, the computation of the matrix vector multiplication becomes particularly simple, which is the central topic of this class. But before that, let me first finish what we left last time, which is about determinants. Remember the warm-up problem last time was determinant of A times B equal to the determinant of A times determinant of B. We haven't proved that yet. But while trying to prove this, I realized that there is something called elementary row. We talked about elementary row operation, but what I didn't talk about in the class was each elementary row operation, one of the three, add a scalar multiple of a row to another row, exchange two rows, and scale one row, can all be written in terms of matrices. These are called elementary row operation matrices. And using the elementary row operation matrices, we'll be able to prove the formula I talked about. But this is a little bit long story. I don't want to take too much time of this class, and therefore I've asked all the GSIs to cover that. Most likely they're going to cover in tomorrow's discussion session, but if that's not possible, cover in Thursday's session. And I've already sent out email, and I hope all the DSIs have sent you the announcement how the discussion session should be handled online. So there's some plan. And any questions about logistics? Okay, so there's a lot of uncertainties going on this weekend. Hopefully, passing Wednesday, we'll know much better how this whole system works. So now I'm going to assume that we have proved this important formula, determinant of A times B equal to determinant of A times determinant of B. As I said, this will be covered in discussion. So I'm going to show you an application of this formula called Cramer's rule. So what is Cramer's rule? You have different ways of formulating that, but the basic idea is how do you compute the ratios of two determinants? So let's pull it. So let's say there are three matrices. There's A, and there's I prime, and there's A prime. Okay, so there are three matrices where A prime, I prime, the n by n matrices, and A prime, they differ only by a column. What does it mean? It means that if A is A1, A2, AN, then A prime equal to A1. Let's say they differ by the ith column, so AI minus 1, and replaced by some other vector called B, the ith column. And then I have AI plus 1, AN. So they're two closely related matrices. Two closely related matrices, and only the ith column is different. So no, I didn't say how to compute this, how to compute the determinant of A prime divided by determinant of A. So it is the ratio of two determinants. So we'll talk about why do we care about this ratio later. Well, if you want to compute the ratio, you say, that's easy, because I can compute the determinant of A prime and the determinant of A, respectively, and I just compute the ratio of two numbers, which is perfectly reasonable. And the Cramer's rule says that there's actually a little bit easier way to compute this ratio. And it later we're going to show it gives rise to an alternative formula for representing A inverse. So using the product rule, so as we start from let's see, let me move this thing here. So we start from no. So I just delete that. So we start from A prime, A times I equal to A prime. This is equivalent to saying that, assume A is invertible, so A invertible. A invertible guarantees the determinant of A is not zero. This is what we showed last time. If A is invertible, then the determinant of A is not zero. So the determinant of A can be put indeed in the denominator. Invertible, so I can write I prime, so equal to A inverse times A prime, right? So, times A prime. So the ratio, let's say I want to look at the determinant of I prime. So using the formula above, it is the determinant of A inverse times determinant of A prime. So this is using product formula. So how this related to the ratio we talked about before? Recall that A times A inverse it always is equal to identity. It's called IN. So I can again apply product formula. So this means determinant of A times determinant of A inverse equal to determinant of IN. But this is identity matrix is 1, 1, 1, 1 on the diagonal. So it's just the product of all ones, which is 1. So then the determinant of A inverse is equal to determinant of A minus 1. So the determinant of an inverse matrix is just nothing but the inverse of the determinant. So combining this one and this equation, we find that, so what we want is really this matrix is the determinant of I prime. That is equal to this ratio I promised to compute. Any question? So it's just the two uses of the product formula. Okay, so now we have reduced the problem of the ratio to the problem of computing this particular matrix I prime. Why do I call it I prime? So let us look at what this I prime is. So this I prime is, now let's take a look. I prime is what is A inverse times A prime. So this is A inverse times A inverse times A1 B AN. What is that? So A inverse times A1, this is just the first column. This is just the first column of the identity matrix, because A times A inverse times A is identity, and this is really the first column of A, so this is just the E1. Okay. So A inverse times the first column of A is guaranteed to be 1, 0, 0, 0, 0. So this is da 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 to EI minus 1. Here I have X, which is X equal to A inverse B. So the ith column of I prime is actually the solution to the linear system AX equals to B. And then I have I plus 1, I EN. Let me write this more clearly as a matrix. So this is 1, 0, 0, x1, 1, x2, 1, 0, and this is x I, no, sorry. So this is 0 to the xi and 0 xn 1. 0, 0, 0, 0. Okay, so other than the ith column being replaced by the solution X, the rest of them are the same as the identity matrix. So now I compute the determinant of this one. How do I compute this determinant? Remember the cofactor expansion. We can expand it with respect to any row or any column. And I want to pick the row or column so that, let's say, if I pick a row, I want to have as many zeros as possible. And after that, the corresponding column to be eliminated has as many things as possible. So I choose to expand the ith row because the ith row, there's just xi, and it will allow me to eliminate all the rest of the stuff. So the determinant of I prime equal to xi times -1 to the I plus I with a determinant. The rest of the things is nothing but an identity matrix, which is I and -1. Why is this so? Because the I prime is obtained by replacing the ith column of identity matrix by something else. I've crossed now the ith column, and the remaining thing is identity matrix. Any question?
Can I ask a quick question?
Yes.
What is I prime and A prime?
Okay, so the question is, what is I prime and A prime? Yeah, so the derivation is a little bit long, so let me record the setup again. So I prime is this matrix given by A inverse A prime, and A is some matrix that is invertible, and A prime is a matrix that differ with A only in the ith column. That's my setup.
So I prime doesn't necessarily have to be the identity matrix?
I prime, as we derived above, the question is I prime does not necessarily equal to the identity matrix, and is not, as we just derived here. We see that I prime is very close to be an identity matrix, but the ith column is actually different. Okay, this seems to work. Any question? Yeah.
Why is the equation will be negative 1 to the I plus I?
Could you repeat?
Why is the negative 1 to the I plus
I plus I. The question is why you have a negative 1 to the I plus I. This is given by the cofactor. So it is the ith row and the ith column. So before you compute the minor, there is a factor there, -1 to the I plus j. You can check the cofactor expansion.
But would it be always positive?
Yeah, it is. Yeah, that's part of the point. Yeah.
So each is an arbitrary column.
The question is whether B is just an arbitrary column. The answer is yes. Okay, so this is just xi. Okay, so what have we derived? What we derived is that, I mean, this I can be anything. This I can be anything, any 1 to n. So this is the so-called Cramer's rule. What it says is, in order to compute this ratio, where A and A prime differ in the ith column, they only change by 1 column. This can be computed by solving one linear equation. So on the left-hand side, this is ratio of two determinants. on the right-hand side is the solution of a linear system. So Cramer's rule reveals a somewhat surprising connection between these two objects, where this xi is the ith component of the solution ax equals to b, and this is the ith component. This is the so-called Cramer's rule. So, any questions? So, where this can be used? There are two scenarios where this is used. Traditionally, this gives rise to the alternative formula for representing matrix inverse, which I'm going to talk about in a second. But that formula only mainly has theoretical value. In practice, you never do that. You just do Gauss elimination or converting to, AKA converting to low echelon form, which is way better. But there is a practical need for computing the ratios of determinants. I won't write it down because most of you wouldn't have that knowledge or the background. In some Monte Carlo simulations, you might want to, the formalism requires you to compute the ratios of two matrices exactly in this form. For example, if you're familiar with Gaussian distribution and the multi-dimensional Gaussian distribution statistics, and the normalization factor would involve a determinant in front of that Gaussian. And it appears in other cases as well. And in the Monte Carlo simulation, what is Monte Carlo? Let's say you have a polymer, okay, so you have a chain of things, and it just gets evolved from one step to another, to another. So if you move all the particles at the same time, it will very likely to lead to a configuration that is so-called unphysical. Numerically, what is happening is that your proposed move will have a very high probability to be rejected by an algorithm. So to make it viable, what you often do is you have like a snake and consists of a bunch of beads, and you move one bead at a time. And that would often correspond to exactly change a column of a matrix. So now you want to compute the ratio of the two that is related to the so-called acceptance probability. And now Cramer's rule will be very helpful because it tells you instead of computing the entire determinant, is actually solving the equation simply. So this is just one example, but it's tons of background information, so I don't want to write it down. Just to let you know that this formula, which is this presentation, computing the two ratios of determinants closely related, different by one column. Few columns, they do appear in practical applications. Now I'm going to follow the textbook, which is to show you a practically useless formula for matrix inverse. But this is the standard way, which is another formula for A inverse. So the idea is the following. What is A inverse? The jth column of A inverse is the solution of the following linear system, that is AX equal to EJ, right? So I just solve the first equation, E1, 1, 0, 0, 0, E2, 0, 1, 0, 0, 0, and I put them together, I will get my A inverse. So, so this immediately tells you that I just look at any arbitrary A inverse ij. J, the J index corresponds to here. So I, look at the Cramer's rule, is here, which means that I should replace the ith column. Okay, so this is equal to xi. And this is the ratio between the determinant of A and the determinant of some matrix, which is given by A11, AN1, da da da. Here it is the ith column. And this is 0, da da da, 1, da da da, 0, A1n, ANN. So what I'm doing here is to replace the ith column of A by EJ. Following Cramer's rule. Now I do the product formula. I do the cofactor expansion again. So I expand the ith column, and you find that this is nothing but the cofactor Cji. Note that the two indices, j and I, got transposed because I'm looking at the jth. This is the jth row and the ith column. The jth row is because EJ, and ith column is because of Cramer's rule. So this is for any A inverse IJ. So it gives us a very compact formula, which is A inverse A equal to the following matrix: C11, C1n, da da da, CN1, C1n, da da da, CNN. So this is the reason why I use a highlight there, is because this is the transpose of the cofactor matrix. It's a beautiful formula, and saying that in order to compute A inverse, each entry is actually given by the cofactor, some cofactor, divided by the entire determinant. And it's practically useless, is because computing, as I said, solving an equation is way faster than computing cofactors. Any question? Okay, so this wraps up chapter 3, and in the remaining 20 minutes or so, I'm going to talk about chapter 5, that is eigenvalues and eigenvectors. So what is eigenvalue? So let's consider so A eigenvalue and eigenvectors. So let's say I have an A that is Rn by n, and I give you a vector x in Rn. Now I consider the matrix vector multiplication. So y equal to A times x. So generally, so let's say in R2, the picture would look like this. So this is x, this is AX. I mean, it's just some other vector. So this is called y, AX. Generally, when I apply a matrix to a vector, both the length and direction of x are changed. There's no particular reason. I mean, maybe some particular A identity matrix, or for some particular x, I mean, the length didn't change or direction didn't change, so on and so forth. But generally, they must both change. But you have seen in the warm-up example that for that matrix 1, 2, 2, 1, I could indeed find a vector so that the direction doesn't change and only the length changes. That is really convenient because that reduces a matrix vector multiplication, which is complicated, to a scalar vector multiplication, which is trivial. How do I formulate this? So the question is whether I can find such an x such that AX does not change the direction. So pictorially, looks like if this is x, I pick a particular x, AX is linearly dependent with respect to x. You might ask, why don't I ask the question in a different way, which is I find an x such that AX can arbitrarily change the direction but not change its length. The answer is this is generally not possible. Let's say A is 2 times identity. Then for every vector x, it just expands its length by a factor of 2. So that question is certainly right. So let's just discard that question from the beginning. And we try to ask the other way, which is whether generically, you give me any x, I can find I can find some directions so that it just becomes a scalar multiplication. I mean, the moment I ask this question, you should immediately try to think about whether there are counterexamples where there will never be such directions. Then the answer is obviously yes. Say in R2, my matrix is a rotation. I just rotate everything by 30 degrees. By definition, there is no non-zero vector, so that after rotating 30 degrees, it's still the same vector unless it is 0. So this question itself has its limitation, and you say, okay, let's skip this chapter and move on to the next. It doesn't work that way. It turns out that the question I just said, find an x such that AX does not change direction, is much, much more general, although it is not ubiquitously applicable. And this is really the central topic of this chapter, which is if there exists such a set of directions, how do you find them? And how do you know that such directions don't exist? So let's write it down more mathematically. I say I have a vector x, and I have AX. The two lies, I mean, they're along the same line. In this using the language of chapter 4, we know that these two vectors are linearly dependent, but we only have 2 vectors, so one must be a scalar multiple of the others, which is, this is just equivalent to, I just literally translate this sentence to the formula, and this becomes AX equal to lambda x, okay? When such relations hold, then we call lambda an eigenvalue. Eigen is a German word, which means characteristic. And X means is an eigenvector. So in the warm-up example, X equal to 1, 1 is an eigenvector corresponding to eigenvalue 3. So now let us look at some examples and try to give a matrix, find all its eigenvectors. So let's use the example we talked about before, A equal to 1, 2, 2, 1. We have found one eigenvector. So one eigenvector is 1, 1 with eigenvalue lambda equal to 3. Without loss of generality, in this chapter, we're going to use lambda to denote the eigenvalue. And how do I find another one? At this moment, let me just show you that there exists one. It might seem magical, but later we're going to learn how to do this more systematically. So another eigenvector is 1, minus 1. Why? Because we can check. Finding an eigenvalue at this point is still difficult, but checking whether it is an eigenvector is really simple. You just apply A to the vector, and you found it's a scalar multiple of the vector, then you're done. This is like, so far it's like factoring a large prime number is difficult, but multiplying two prime numbers is really, really simple. So, but later we're going to learn that it is diagonalization is way simpler than factoring to a two prime number, factoring a large number. So this one is, we just compute. This is 1 times 1 minus 2, so this is minus 1. This is 2 times 1 minus 1, so this is 1. So this is a minus 1 times 1 minus 1. So this is indeed an eigenvector corresponding to lambda equal to minus 1. Any question? So yeah, from now on, when I say any question, it automatically implies any question remotely. So okay, so what's the significance of finding two, of course, linearly independent eigenvectors? Is that they actually span a basis in R2. So because we found 1, 1 and 1 minus 1, they are linearly independent. So it forms a basis B in R2, 1, 1, 1 minus 1 in R2. What's the importance of forming a basis? It means that any vector in R2, okay, we started from finding this very simple vectors, but once you found a basis in R2, then any vector X can be expanded in terms of the linear combination of R1 and R2. So let's just call this one called B1, this one called B2. Then any vector X in R2 can be written as some linear combination of B1 and B2, where C1 and C2 are real numbers. Let me further say, denote by the eigenvalues. B1 corresponds to eigenvalue lambda 1, B2 corresponds to eigenvalue lambda 2. Then now you see, how do I compute AX? AX, by linearity, is just a C1 AB1 plus C2 AB2. And I can use association rule. AB1 is nothing but lambda 1, B1. AB2 is nothing but lambda 2, B2. You see, this so-called eigenvector decomposition, or eigen decomposition for short, really simplifies general matrix vector multiplication and replaces by vector, scalar multiplication of vectors, and just add them together. The beautiful part is the decomposition, or this way, which is apply A individually to the eigenvectors. It doesn't depend on dimension. It can be applied to any Rn. So this is, let's say, if I want to compute, give me an x, I ask you to compute a to the 1,000 times x. I really don't know how to work this out. But if you give me the eigen decomposition of x using this coefficient C1, C2, then this just becomes C1 lambda 1 to the 1,000 times B1 plus C2 lambda 2 to the 1,000 times B2, and problem solved. Any question? Okay, so let me rewrite this two-dimensional decomposition as follows. So we know A B1 equal to lambda 1 B1, A B2 equal to lambda 2 B2. I can write it in a slightly better way. I form a matrix B, I form a matrix V to be B1, B2. So this is a 2 by 2 matrix. I concatenate the two things. I form a diagonal matrix, lambda 1, 0, 0, lambda 2. I'm introducing no new information, just to reorganize this thing a little bit. And then you can immediately check the following fact is true. A times V equal to V times D. Why? A times B1 equal to B1 times lambda. So just a 2 by 2 matrix multiplication, and you'll be able to find it. Furthermore, because V is a basis in R2, V is a basis means every column has a pivot. So every row has a pivot, and therefore V is invertible. V is invertible. So A equal to, so which means V inverse exists. I now right multiply this equation by V inverse. I have A equal to V D V inverse. Or this is equivalent to saying that D equal to V inverse A V, if I left multiply by V inverse. Now you see, I use an invertible matrix and have converted a general matrix A to a diagonal matrix called D. And therefore, this procedure is called diagonalization. This is a really important technique. that is both conceptually important and practically important. There's numerous applications in almost all fields. Let's stop here, and I will see you virtually on Wednesday.